In this video, I want to present the concept of sheet resistance and series and parallel resistors. In a previous video, I said that resistance is equal to rho, which is the resistivity of a material, times the length of the resistor divided by the cross-sectional area of the resistor. Now, if I have a thin sheet of material with a thickness that I'll call T, and a width that I'll call W, and a length that I'll call L. This is the length. Now, the length is always in the direction of the current flow. So in this resistance material, the current is flowing in this direction. So let's rewrite this equation for this particular sheet of material. The resistance is equal to the resistivity of the material times the length in the direction of the current flow, and in this case it's divided by T times W, which is a cross-section that the current flows through. If I take these two terms here, the resistivity and the thickness, I can rewrite this equation. R equals resistivity divided by the thickness of this sheet times the length divided by the width of this resistor. This term here, the resistivity divided by the thickness of the material, is called the sheet resistance. And I'll call that R sub S. Now this next term, the L divided by W, is the number of squares that the material has. For example, if I have a square and another square for my resistor, and this is the length, and this is the width, and again the current is always in the direction of the length. Current flows this way. I can divide L by W and I get two squares. One square, two squares. So my L divided by W is 2 squares in this example. Now let's say, for example, I want to have a sheet resistance that's equal to 100 ohms per square. So if I have 100 ohms per square and I have 2 squares, then my total resistance will be the 100 ohms times 2, which in this case would be 200 ohms. Let me erase this. Let's do a sample problem. Let's presume I have a material that has a resistivity that is equal to 2 times 10 to the minus 4 ohm meters. And let's presume that I want to take this material and I want to make a resistor, a very thin resistor that has a sheet resistance of 100 ohms per square. Now sheet resistance, R sub S, is equal to rho divided by the thickness of the sheet, T. Now I know that RS is 100 ohms per square, and I know what rho is, so I want to solve for T. So let's transpose. T is equal to rho divided by the sheet resistance, RS, in this case, is equal to 2 times 10 to the minus 4 ohm meters divided by sheet resistance of 100 ohms, which is equal to 2 times 10 to the minus 6 meters, which is also equal to 2 microns. So if I have a material with a resistivity of 2 times 10 to the minus 4th ohm meters, and this material is 2 microns thick, I have a material that has a sheet resistance of 100 ohms per square. Let me again erase this. Now let's use this material that's 2 microns thick and make a 200 ohm resistor. So I can take this material and I can lay down 1 square, and I know that that's equal to 100 ohms. Let's add another square, and now I have a 200 ohm resistor. This is 100 ohms, 100 ohms, and I have a resistor terminal at this end and this end, so my current is flowing in this direction. So the length of the resistor is this dimension, and the width, W, is this dimension. So I can solve for my resistor. Resistance is equal to the sheet resistance times the length divided by the width. And in this case, the sheet resistance is 100 ohms, and my length is twice the width. I have 2 squares. So this is 2, number of squares. This is ohms per square, sheet resistance, and I have 2 squares. So my squares cancel, and I have 200 ohms for the resistor. Let's take the same resistor, the same shape, and let's put the terminals at this end instead, so that the current will flow in this direction. So now this becomes the length, and the width is this dimension. So what is the resistance of this material? It's the same shape, but the current is just flowing in the opposite way. So again, I can say that the resistor is a sheet resistance, which is 100 ohms per square, times the length divided by the width, or the number of squares. The number of squares is 1/2 of a square. And again, the squares cancel, and I'm left with 50 ohms. So this is a 50 ohm resistor if the current flows in the short dimension. So if I want to make a 100 ohm resistor, I can take 1 square of this 2 micron thick material. I can add another square. And my terminal is here and here. So schematically, I could call this 100 ohm resistor here, 100 ohm resistor here, and I can draw this in terms of the resistor symbol. So I have 100 ohms in series with another 100 ohms. So 100 ohms and 100 ohm resistor here produces an equivalent resistor of 200 ohms. So I can say that 200 ohm resistors in series add together. So what this tells us is that series resistors add. So these 200 ohms add up to 200 ohm total. So this is series. So now I'm going to take the same resistor shape, these 2 squares of resistance, and I'm going to put that down here. So we know, since this is 2 squares, that this is equal to 200 ohms, and again the current is flowing in this direction. Now let's take the same material and double this dimension. We'll add another 200 ohm resistor here. And again, the current is flowing in this direction. So now I can draw the schematic for this. This is a top resistor is 200 ohms, and it's connected in parallel with the bottom resistor that's also 200 ohms. 200, 200. And since this forms one square, and the sheet resistance is 100 ohms per square, I know that the equivalent of these two parallel resistors is 100 ohms. So the neat thing about sheet resistance is that any square, I can just look at this square, and I know that if the material is 100 ohms per square, that this is a 100 ohm resistor. And it doesn't matter how big the square is. If I have a bigger square here, this is also 100 ohms. If I want to make a 200 ohm resistor, I just add another square. If I want to make a 300 ohm resistor, I add another square. If I want to make a 400 ohm resistor, I add another square. So terminal, terminal.